All right, everyone, let's get to work. So I think I'm going to omit chapter 6. We talked about that last time, so I'm going to get rid of the chapter 6 quiz and remove questions on chapter 6 from the test. Yeah. Yeah. No problem. Yes.
So the problems from quiz 6 won't be on the midterm?
They will not be on the midterm. Yeah. So I'm going to go through and delete them this afternoon. Yep. But it is going to be. So right now it's 70 questions. I guess I'll decrease it like 65 or something. Yeah. Okay. So it'll be 65 questions in 2 hours. Open book, open notes, 1 through 5, and then chapter 7. So we need to get through more stuff in chapter 5 actually before I get to chapter 6. So let's do some chapter 5 back of the book exercises. This Sunday, the 15th. Yeah. It's open today. Yeah, it's open right now. I just got to change it to get rid of chapter 6. I think the syllabus says week 5, and the quizzes are saying week 4. It should be the 15th. Yeah, so I'll change that in the grade book. I'll change it. All right, so what did we do last time? We did, essentially, we did the theoretical kind of the different types of functions, right? The linear function, the Leontief function, the Cobb-Douglas function, and we talked about, the partial derivatives, yada, 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 right? So now let's actually do some examples. So this is number 1. This is page 167 in the text, and it gives us a particular production function. And the first thing we're asked to do is calculate the average product of labor when the capital is fixed at 81, the labor is fixed at 16. So how would we calculate the average product of labor? So anytime we have an average, right, that just means that we're taking the Q and we're dividing by something, right? So the average product of labor is going to be equal to Q divided by L, which is equal to F of K and L divided by L, which is equal to K to the 3/4 L to the 1/4 divided by M. Everybody with me so far? Okay. So now, whenever we take something from the denominator to the numerator, the exponent turns negative, right? So if we have 1 over x to the a, that ends up equaling x to the negative a. Right? That's just a property of math. And so we're going to do the same thing here. We're going to say k to the 3/4, L to the 1/4, L to the negative 1. I can rewrite that as k to the 3/4, L to the 1/4, L to the negative 4/4. And then remember, whenever we have x to the a over b times x to the a over b, that ends up equaling x to the a plus a over b. So using that same thing over here, what do we end up with? K to the 3/4 L to the negative 3/4. And then if we want to, we can go ahead and get rid of that negative exponent and have this be equal to K to the 3/4 over L to the 3/4. So this is one way that we can do this question, right? Where we calculate the average product of labor just in terms of K and L, and then we plug in the K and L that we're given, right? 81 and 16. Okay? So this would be equal to 81 to the 3/4 over 16 to the 3/4, which is just equal to 4. So you can always just Google it. Divided by 16 to the 3/4. Boy, 3.375. Let's. You think I got a parentheses, fellow? Yeah, good. 3.375. All right, so that's one way to do it. What would be the other way to do it? Well, the other way might be a bit easier. We can just evaluate this function. Oh, yeah. No. But see that's not always going to be the formula for APL. That's only the formula for APL for this functional form, right? Where it's K to the 3/4 L to the 1/4. So you don't have to show each step though, like I did here, right? Like I did a lot of it. You know, I put a lot of extra steps in there that you could skip, but I would say it'd be very difficult to just go from this to, I guess it's not that difficult. You just end up dividing by L and just subtract the exponent from the, you know, like, so you could probably do it in your head. But yeah, so it ends up being essentially the same thing as what you started out with, but the L pops on the bottom because it's the average product of labor, so we're dividing by labor. And since the numerator, these values are always less than 1, so since we're dividing by L and there's going to be an L to the negative 1, and that means that since this is always less than 1, the L to the whatever, when you combine them, is always going to be negative, right? And so that's why it's going to flip onto the bottom. The exponents are going to be different depending on the starting exponents you're given. Does that make sense? So for instance, what if, so let's just go quick, what if the formula was, sorry. So the most common type of formula here is K2. I'm just showing, no, sorry, I'm having us do practice. So let's do the same exact thing, but for these exponents. So on your own, what's the average product of labor for this? We don't need values yet. We're just finding the formula. Well, where's the L 1/3? On the bottom. So K 1/3 divided by L 1/3.
Okay, so as long as it goes to the bottom, as long as it goes to the bottom, you just erase that.
Anytime you move it from top to bottom or bottom to top, the sign flips of the exponent.
Okay, so it's
So in the end, it should not be negative.
So did I just write this wrong? Because I have like L -3/4 and then L 1/4. I don't get what it's.
L -3/4. L. Wait, did I write it wrong? Yeah, you wrote it wrong.
Oh, so this is.
This should be 3/4.
L. Okay, that meant thank you.
Wait, huh? You broke the rules of that. All right, so let's walk through it all together real quick, okay? So the average product of labor is always going to be, this is equal to Q, right? So it's my Q over the L. So this is going to be K to the 1/3, L to the 2/3 over L to the, we'll just call it 3/3 right away, right? Just so it makes it easy when we're doing the fractions. Then we have K to the 1/3, L to the 2/3, L to the -3/3, right? Because we pull this guy up, so it becomes negative. Then we're going to combine these, since they're both base L. Yes?
Sorry, but this one,
Yes.
this whole,
Because the fractions of the last one were out of 4. Everything was in terms of 4 in the denominator. And so remember, when we add fractions, we have to have the same denominator. And so that's why I did 3/3 or 4/4. So yeah, so I'm just using whatever fraction is equal to 1 with the same denominator. And so then we're going to add these fractions up together. So we're going to equal K to the 1/3, L to the -1/3. And then we're just going to put this guy on the bottom equals K to the 1/3 over L to the 1/3. Can you what? Yes, and then from here you can do K over L to the 1/3. Yes, absolutely. And the property of our exponent. So that was our practice. So now the other way to do it is, so let's go back to this, right? And so the other way to do it is essentially just to plug in the 81 to the 3/4, the 16 to the 1/4, and then divide by 16. And so you can do this as well. You don't have to do all of the algebraic manipulations and stuff, right? You can just plug and chug. So why are we just dividing by 16 to the 1 power at the bottom? Because we're only just dividing by L, because that's just the definition of APL. Does that make sense, everybody? All right, so what about the marginal product of labor? So I want you guys on your own to calculate the marginal product of labor for this particular one, for the K to the 3/4, L to the 1/4. So what's the formula for the marginal product of labor? It's not the average, it's the marginal.
Yeah. Yes.
Yeah. Okay, capital. So it's the machines, it's the tables, it's the building that you're producing in, right? You know, so essentially all of production takes a certain amount of capital and a certain amount of labor, even if the capital is just like land that you're standing on. But it could also be the computer you're using, pen and paper, a telephone, a cell phone, right? That's all capital, right? And so the labor is the human operator, because if the capital is just by itself doing nothing, you know, it's not going to be producing much, right? So they're both necessary. That's what this is. And there's substitutability between them. If one of them becomes really expensive, we can, so if all of a sudden labor becomes really expensive, we could just get more efficient machines, right? We've been seeing this with, you know, Panera Bread and other stuff like that, right? They're making it so that you order now with a kiosk, and the same thing at Chili's, right? You have a little like freaking iPad at your table, you can pay your bill on it, you know. So they're creating all of this, what's called labor-saving technical change. And so you keep on upgrading your capital because labor is getting more expensive, everything else is. Oh yeah. All right, so I've done the steps here. Get the marginal product of labor. So we take a partial derivative of the total production with respect to labor, which means that we set anything that doesn't, like any other variable or whatever, right? We just kind of set that aside, right? So that's why I put it in this bracket box. We just copy and paste this down, okay? So we keep it there, and then we just take a derivative with respect to L as if there wasn't an extra variable in this equation, right? And so if we had x to the 1/4, the derivative of that is 1/4 x to the negative 3/4. So that's the same exact thing that we're doing here in terms of we have L to the 1/4 initially, and then we end up with 1/4 times L to the negative 3/4, right? That's because we're subtracting 1 from 1/4, which is just part of our extended power rule. So then the rest of this is really just resolving that. I'm just pulling the 1/4 out to the front. I'm setting this k in the middle, the L to the negative 34s here. There's two different ways you can write it. You can either leave the k to the 3/4 on the top and then put the 4 and the L to the negative 3/4 on the bottom. Or as G so nicely pointed out, you can also just have it be 1/4 times k to the 3/4 over L to the 3/4 or 1/4 times k over L to the 3/4 altogether. Okay, so you get derivatives though, and so do you understand this though? How we get to x to the negative 3/4? Okay, so here let's just redo this. So you understand how I got to this one? Kind of. Okay, so it's the same aspect of this, right? Because this 1/4 x to the 3/4, that's the same exact thing that's going on right here, just with a different one, right? We're taking what's called a partial derivative. So what that means is we only care about what happens to an incremental change in L. We don't care about what happens to an incremental change in K. So we're not going to be doing any of the power rule stuff that we are doing for the L, right? The L to the 1/4, we're not going to be doing that for the K to the 3/4. We're just copying and pasting the K to the 3/4 from the initial equation, almost as if it's a constant. And it's just going to be just plopped down at the beginning there and unchanged, right? And so that's just going to be multiplied by whatever the derivative part is that we end up doing. Marginal product of labor, exactly. So the next we'll do marginal product of capital, and you'll see that one next. That one we're going to leave the labor alone and copy and paste that labor part. So this is just asking us about what's the extra output I get from adding one more labor unit. So, but here I'll still do this again. So we've got so k to the 3/4 brackets 1/4 L to the, and then again it's 1/4 minus 1, right? So that's just L 1/4 minus 4/4, which ends up being negative 3/4. And so then we got to pull these things down though, right? And so this ends up being, we can switch the order, 1/4 k to the 3/4 times L to the negative 3/4. So we all with me still there? Okay. So now we're going to put this L on the bottom. Okay. So flip that L on the bottom. We end up with 1/4 times k to the 3/4 over L to the 3/4. And then because of the property that if we have x to the a over b divided by y to the a over b, that equals x over y to the a over b. So that's a property of exponents. And so because of that, we can then say this equals 1/4 K over L to the 3/4. Okay, awesome. So now, do the marginal product of capital. Can you show the clocks?
Oh yeah, but I don't know. Okay, so like.
And you're writing small.
Yeah, I'm sorry. That's why I did. Okay, let me ask you first, and then you go that.
Yeah.
Okay, so.
Pressures.
Okay, so this 1/4, I thought we did the improvement thing.
Oh,
Then
yeah.
why do we still have it there?
Because it doesn't go away when you do the derivative.
Okay, it's still there.
It's still there, yeah. So it stays there, and it's the constant. It's like when you take derivative of x squared, it's 2x, right?
Yeah.
And so it's the same thing. This is the
Okay.
2. You have to multiply by 1.
Okay.
So
So
it has
then
to stay there.
it stays there even.
Yeah.
Okay.
Yeah, definitely. Yeah, so whatever that initial exponent is on the thing that we're taking the derivative with respect to is going to end up being the constant for these particular type of Cobb-Douglas production functions. They don't start out with a constant. Yes, and Leontief. And Leontief. Which, if we don't get to today, we'll definitely cover in class on Wednesday with question 9. All right, so that was B. All that stuff was B, question 1. Now let's talk about C. So we're told capital is fixed. Do we have any other questions on the marginal product of capital before we move on? Okay, so we're told that capital is fixed at 81 units. We're told that the price of the good is $200, and we're told that the wage is equal to $50 per unit of labor. So now we are asked, how many units of labor should they hire to maximize profits? So who knows the equation that we need? W is wage. So who knows the equation that we need to maximize profits with respect to labor? So the equation that we're always going to use is we set W equal to the value of the marginal product of labor and then we solve for the labor star. The labor part that maximizes profits. So what is the value of marginal product of labor? We calculated the marginal product of labor. What's the value of marginal product? Price times marginal product. So this is equal to price times marginal product. So we know that our marginal product of labor is 1/4 K over L to the 3/4. So then our value of marginal product of labor would be equal to price times 1/4 K over L to the 3/4. And we know that we have to set this equal to the wage. All right, let's get to work. So we're told the wage is $50. We're told the price of the good is 200. We're told the capital is fixed at 81. And we're trying to solve for L. It's 81. So what's the only value of L that's going to give us 50? So since this is 50, then the only value of L, we need this whole thing to be equal to 1, right? Must equal 1. And so since this whole thing must equal 1, then this has to equal 81. So that we get 81 over 1, which is equal to 1. Okay? So not the hardest of problems they gave us here. Let's try another one. because this 20 times 1/4 equals 50, which is equal to 50 here. Let's do another one similar to this. Let's do number 13. Any questions on this? Depending on the functional form, depending on the exponents of the k to the... Yes, exactly. All right, so we are the manager for Herman Miller, manufacturer of office furniture. We recently hired an economist, worked with engineering and operations experts to estimate the production function of a particular line of office chairs. The report indicates that the production function is equal to Q equals 2 times K to the 1/2 times L to the 1/2. Where K represents capital and L represents labor, your company has already spent a total of $8,000 on 9 units of capital. Due to the correct economic conditions, the company does not have the flexibility. Due to the current economic conditions, the company does not have the flexibility to acquire additional equipment. If the workers at the firm are paid a competitive wage of $120 per day, and shares can be sold at 400 buckaroos each, what is the profit maximizing level of output? And what is the profit maximizing labor usage? And then what is the maximum profit? We always use I as profit. We also use it for inflation. I think there's enough. It'll tell the problem will tell. I'm going to guess because this is managerial economics, it'll almost always be profit and not inflation. We're not really doing too many macro. Good question. This L? Sorry. Well, yeah, K is 9. So we're going to use the same profit maximizing equation as the end of last one. So what did we do? What was the first thing we did? We set the wage equal to the value of the marginal product of labor, right? That's our first step to solving for the optimal amount of labor. And then we can figure out the optimal production, and then we can figure out the optimal profit. The profit level. supposed to divide it with 8,000. Oh no, the 8,000 is unnecessary. That's only if we were doing the calculation for the, or well, no, we'll need the 8,000 for later. Sorry, for the total profit, but we don't need it for this calculation. We just need the number, so we're just going to put 9 in for the capital. We just need the units, not necessarily the price of capital. We're solving for L. That's the thing we're trying to solve. Yeah. So questions on how we got to 100? Square root. It just means square root. Ten equals L to the 1/2, so then you have to square both sides. You guys follow my algebra? So that's the profit maximizing L, but we're asked for 2 more things, right? We're asked for the profit maximizing Q, and then we're asked for the actual profit. So how would we get the profit maximizing Q? We're just going to plug this in, exactly. So we're going to say Q equals 2 times 9 to the 1/2 times 100 to the 1/2. So this ends up being 2 times 3 times 10, ends up being 60. Now we know the firm's fixed costs are 800 because, or 8,000 because of this, right? The $8,000 spent on the 9 units of capital. And so when we're doing our profit, it's going to be our total revenue minus our fixed costs minus our variable costs. What's our total revenue? Our total revenue is going to be 120, because that's the price of them, right? Times 60. Oh, wait. Sorry, we get $400 per chair, not 120. 120 is the wage. 400 is the price. So, yeah, let's just redo this. It's 400 times 60 minus the fixed costs are staying the same, right? That's 8,000. By definition, fixed costs stay the same regardless of labor. And then we're going to subtract. So here's our variable cost. This is 120 times the 100 labor, right? So this is my wage bill. This is my fixed costs, my capital equipment, right? And this is my total revenue. And so we end up getting 24,000 minus 8,000 minus 12. And so our total profits end up being 4,000. Pardon? The answer to L is 100. The answer to Q is 60, and the answer to pi is 4,000. You were still on L the whole time? I'm sorry, I shouldn't have jumped ahead of you. I mean, you can. Yeah, to get rid of this 1/2, you just. Yeah. Questions? All right, so in class on Wednesday, I want you guys to know the formula for how to test for economies of scope and how to test for cost complementary. So it's question number 7, top of page 169. That's what we're going to start with. So if you come in already knowing it, then I don't have to teach as much. So the economies of scope equation and the cost complementaries, and we can finish out chapter 7 or 5. We can jump into chapter 7 and hopefully get it done on Wednesday so we don't have to meet on Friday. Question 7, and then also do question 6 on your own, just because it's good practice. So complete the table for number 6, just to understand how all the different costs are related to each other. So do 6 and 7. All right, that's it. Have a good one. Thank you guys. Good work today. I know it's tough, but you guys are getting it. You are getting it. I know it's tough.